Let's close out this short introduction to tropical cyclones with this last part about ensemble and consensus forecast techniques. This is an example of operational global forecast system in orange here, and GFS ensemble member forecasts, which are in these white lines here. Compared to the best track Hurricane Ike here in the black line. In this case, GFS ensemble average performs better than the deterministic GFS forecast. So when you have one single realization, you call it deterministic forecast, and when you perturb the initial conditions, in the TC case obviously the initial position of the tropical cyclone has to be prescribed exactly and from the observations, and then on perturbations of the initial conditions require various techniques around that, which we are not getting into, but this is the same approach used in climate forecasts, weather forecasts, subseasonal to seasonal forecasts, and so on. Some of the ensembling techniques I have in my course on S2S forecasting you can look up, or you can find other material. What happens in general is that when there is a plan to make deterministic forecasts, so one forecast, the resolution can be kept high, especially for tropical cyclones. But when you want to do ensembles, there is a lot of effort needed to figure out how many ensemble members are optimal. But in general, if you have to make multiple realizations in a short time, because cyclone is evolving rapidly and you have to update forecasts repeatedly, then the resolution tends to be degraded, so that has to be kept in mind. So ensembles of members of a single model tend to be seen, depict the uncertainty of that model in forecasting the tracks, in this case also intensities as a forecast, but we will see there are other ways to combine multiple models. So the National Hurricane Center, various models used for ensemble forecasts, the US Global Ensemble Forecast System, Meteorological Service of Canada, CEFS, ECMWF Ensemble Prediction System, EPS, and Japanese Meteorological Agency's Typhoon Ensemble Model. Okay, each model has different resolutions, different ensembling techniques, singular vectors, bread vectors, ensemble Kalman filters, or simple perturbations, and so on and so forth. Their vertical resolutions also tend to be different, and hence skills tend to be different, but the errors in tracks and intensities are considered random, and in general, when you produce consensus or multi-model ensemble forecasts, then those errors tend to get cancelled. So the skill of the ensemble mean for a single model is better than ensemble members, and skill of multi-model ensembles or consensus forecast tends to be better than individual models as well, because of this cancellation of errors. Of course, there are various ways to do the ensembling, can be linear average or weighted averages and so on, and sometimes you have to discard models which are doing completely crazy, for example, so there is some subjectivity involved there as well. So that's multi-model ensembles and consensus forecasts. This is an example of Hurricane Ophelia, which did some crazy loops off of Florida and then Georgia and North Carolina, I think. You can see that here approximately. There are better images on Wikipedia if you want. So this is the National Hurricane Center best track for Hurricane Ophelia in 2005. Loops off of Florida, Georgia, and South Carolina coasts resulted in widely divergent operational forecast model track forecasts, which we will see next. So you can see the various stages of the storm, and this kind of looping is not typical, and models obviously did not necessarily capture it, especially in the forecast mode. So this image is not tremendously good, but Hurricane Ophelia early cycle track guidance for 7th to 9th you can just say that the various track forecasts were not agreeing with each other. So this is various days here, 7th, 8th, 8th, 9th, then it transitioned into an extratropical cyclone. So consensus forecast or ensembles of a single model can be tricky when the cyclone doesn't behave as expected. So those are 120-hour forecasts of Hurricane Ophelia initialized at 6-hour intervals. 1200 UTC 7 September to 0600 UTC of 9th September 2005, the track guidance. Official forecast is given in black. See the legend to identify individual numerical models, so multiple models are involved. So official forecast was in black, which you cannot even see very clearly here, and there are the different models involved in the forecasting. Okay, there is another model which takes these consensus. So why we will see why we need to spend the effort to make consensus forecasts, because it's not just a matter of taking different outputs and averaging. It takes a lot of work, so we have to have some payoff for doing that. But in terms of uncertainties and track errors, there is prediction of track error by Gore's prediction of consensus track error. GPCE provides a measure of uncertainty in the consensus track forecast that is better than the standard approach based on forecast skill of previous storms. Okay, typically you make track error estimates based on model performance for the past cyclones, but this one does it in this way. Intuitively, you might expect a large spread in the model forecasts. Intuitively, you might expect a large spread in the model forecasts could lead to a large forecast uncertainty and potentially large track errors. Also, differences at initial forecast time point to uncertainties that could affect the forecast. Following this logic, Gore's produced this predicted consensus error product, which depends on a combination of consensus model spread, difference between each ensemble member, and the ensemble average for a chosen metric, such as latitude, longitude, and intensity. Initial and forecast tropical cyclone intensity, initial and forecasted intensities, initial cyclone location, forecast displacement of cyclone location in terms of latitude and longitude, tropical cyclone speed of motion, and number of members available for the consensus forecast. Okay, so this is an independent estimate of track error. Number of verifying official forecasts for the Atlantic Basin for various lead times from 24 to 120, and this is these are different years, and you can see that there are some years like 2005 had lots of storms, so obviously had lots of verified forecasts. So the interannual variability of the cyclone activity itself is included here when you do this way. So the number of verified forecasts from 2001 to 2007 seasons, the GCPE was developed on a training data set of these data from 2002 to 2006 season. So using past forecasts, track error model is developed, and you can see the forecast error and predicted error. So this is verification of the GPCE calculated forecast error compared to the actual track error of the corresponding forecast conducted on a training data set. So the correlation is pretty good. This is 120-hour forecast error versus predicted error with a stepwise linear regression. So having an estimate of predicted track error is of course very useful, because that can be used to include the information in issuing warnings, alerts, evacuation plans, and so on, disaster recovery and disaster management in general. And this is showing example of GCP forecast circles of the potential consensus track error for a 48-hour consensus forecast of Hurricane Rita in 2005, another example from the record year, initialized at 0600 UTC on 22nd September 2005. The black line is the best track from post-storm assessment, and you are looking at how the models did versus how the GCPE forecast of track errors worked. Okay, so that is from the National Hurricane Center. Okay, details, but nonetheless, GCPE validation for 2005 to 2007 for the Atlantic is shown here. Documentation of the frequency with which actual storm track fell within the GCPE calculated forecast error circle. Recall that 2007 season was not included in the initial. So when you do these kind of statistical tools, you have a training set and then you have a forecast period to make sure that your forecast system is working, right? So there is a significantly high percentage of track errors that fall within the forecast error circle. So the confidence in GCPE can be based on this kind of validation of the forecast model. Okay, just follow that through. Comparison of a track forecast skill for consensus. Various models use that NHC and dynamical forecast models and the official NHC forecast, OFCL. The dynamical models plotted are the member models used in forming consensus forecasts. Basically, this is arguing that models used in developing the consensus forecasts have lower skills compared to the relative to Clippers, but also the consensus, the work done to issue consensus forecasts is worth it because that skill is definitely higher than the individual models. You have to pay attention to the fact that the skill is lower at a shorter lead time than at a longer lead time, and then it falls off again. And that's the official forecast, consensus forecast there. So there are dynamical reasons and initial condition dependence and so on, which can make the initial forecast skill lower than Clipper, because this is with respect to Clipper. Because Clipper has statistical information which can produce better short time skill than the dynamic models, and then at persistence again models lose the initial condition information and so on. Nonetheless, the main message is that work done to use multiple models to produce consensus forecasts is worth it because the skill is systematically higher compared to Clippers, which is our baseline model that should not be used. It's a climatology persistence statistical model, so we have to do better than that. So the skill relative to Clippers is better than that, and that's kind of the story of ensembling and consensus forecast, where ensembling is a single model perturbed in various ways to produce multiple realizations to depict model uncertainties, and consensus forecast is using multiple models to produce a multi-model ensemble forecast. We didn't do the details of exactly how the ensembles are produced and how multi-model ensembles are created and so on, but you can read those up. The techniques remain similar to weather forecast, ENSO forecast, climate forecast, subseasonal to seasonal forecasts, and MJO forecast, and so on.